And on solving that guy, what we get is basically this. On simplifying that expression, we are getting our gain as minus Gm times R, which is basically del V out by del V in. So this is the gain of the fully differential amplifier. And also, now that we have established that the gain of this basic differential pair was this, what would have had been the gain if I would have been taking the output from only one side. So you can again intuitively comment that, let us say that I was taking output at V out 2 only, then I would have just said that GMR by 2 will be common, and then V in 1 minus V in 2. So that basically means that for single-ended amplifier, differential amplifier, the gain would have been GMR by 2, right? Depends upon from where I'm taking the input. If I would have taken input from here, it will be minus GMR by 2. And if my V out 2 is the input, it will be GMR by 2, right? So we now can appreciate the difference in gain between fully differential and single-ended differential amplifier. This is a basic idea about the large signal analysis, and I think we have seen this again and again. So what typically we first see in Razavi's book is this kind of a curve, right? This is the kind of curve you see. And why do you see it so? Because what we are trying to establish from here is that this guy is typically V out 1, this guy is typically V out 2. And what we are trying to say here is that when this transistor, let us say this transistor is V in, or if I were to show on here, if I were to show here, if this transistor is basically off, okay? If this transistor is basically off, then this node will let no current pass through it, and so it will get to VGD, and eventually, when it is allowing all the bias current flow through it, it will eventually fall down to VDD minus I bias times R, and this will be some middle value where it will allow VDD minus I bias by half current to flow through it, and that multiplied by R, right? And this will just follow a similar pattern. Right. So that's the basic idea. And now the question is, if I'm saying this guy is V out 1, this guy is V out 2, so what would be along this axis? That's the question. So here, in Razavi, it is given by V in 1 minus V in 2. So here there will be V out, here will be V out 2, here will be V out 1, but here I'm taking it as V out V in 2 minus V in 1. So I think it's quite evident that why the curves look like this, because when V in 2 is much larger than V in 1, that means basically this guy is almost on the verge of being off and this guy is on. So V out 1 will tend to VDD, and all these things we understand. And here I have just sketched the differential output, and here I have drawn it with respect to V in 1 minus V in 2, and this is the curve we see, right? And if I define it as V in 1 minus V in 2, so here you will see V out 2 and here you'll see V out 1. So that is also not that big of a problem anyway. So we can move further now in our analysis. Here I have again drawn, basically I have tried to draw the gain of the fully differential amplifier, but it also equally applies to a single-ended differential amplifier, just the values where the curve bends will change. And here what I am trying to show is that how will the gain vary with the input common mode voltage. So let us try to have some intuitive picture around it. Again, if I just open this guy and I'm applying some common mode signal, okay? If I'm applying some common mode signal, then initially it is 0. So that means that both of these transistors will be, what will they be? They will, they see here, since I'm forcing this I bias current to, as the net sum flowing through both of these guys, so it has to pass some current. But since the V in CM is low, so it is low. So in what region of operation would you expect it to be? So the thing here is that this I bias current is also implemented by a transistor only, right? And if this voltage, the input common mode voltage is too low, so again it will imply that even this guy is not in saturation, right? If this guy is not in saturation, or which means this guy is in triode, so the current, the ideal current source behavior also will cease to happen. So what basically happens is that until the transistors are both of the transistors, the differential transistors are on, we find that even our NMOS or even our tail current transistor is not in saturation. So you see that your gain is basically very slowly grows. And after this point, when both of the transistors are on and in saturation and the tail current source is in saturation, then we find this gain to almost saturate, which is the kind of behavior we want for a range of V in and for a high enough V in. And for a high enough V in, when the both of the transistors enter a triode regime, the gain again falls. So this was the basic idea also of introducing a tail current source. That was our main motivation. And the motivation typically was that, okay, I think I have sketched something wrong here. I'll explain where the curve ends, but yeah. The main idea here was that we wanted that for a large swing at the input signal, we wanted our gain to be relatively constant, and that is something achieved by adding the tail current source. Now, where will this guy bend? Let us just calculate that also, okay? VTH, I marked it by accident, so pardon me, but let us just actually calculate the values at where the curve should behave that way. So if this is my basic differential pair, this is my transistor M1, this is my M2, and here I have tail current source. I'll for time being define it by transistor only, and this VB is high enough so that this transistor is on. Now, to ensure that this guy is in saturation, here what should be the voltage? Here the voltage should be at least VB minus VT, where VT is the threshold voltage, right? And so this implies that here, what should be the minimum voltage to ensure that this guy is in saturation and this guy is also on? So that should be how much? VB, VB. Yeah, it should be VB. Why? Because it should be at least one threshold voltage greater than this, right? So if it is one threshold voltage greater than this, so we can say that yes, if this is the common mode signal, so then at this voltage we can say that yes, this guy is ensured to be in saturation and this guy is also on. Perfect. And here, since the current flowing is very less because the input, because this guy is just in saturation, because below this voltage, this guy was in triode, so we can basically say that this node voltage is also high because the current value was low. So my point is that when we in CM value just crosses VB, this transistor is both of these transistors already are in saturation. So when we are trying to sketch the large signal picture here, when we are sketching gain with respect to the input common mode voltage, what we will find is that initially when the common mode signal is almost zero, this guy is in triode regime, and thus and thus what we'll see is that the gain will just like really loosely grow, and at the value where here in this case this value happens to be VB itself, we'll find that this guy now finally enters saturation, and now both transistors are also in saturation. We'll find the gain to be constant for a certain range of V in CM, and when the point comes that this voltage is high enough that it basically enters the triode regime, there we find that the gain falls off, right? Because both of the transistors enter the triode regime. So that is the main idea, but we are not finding the exact values here. We can always go to the elaborate analysis and write equations to find the things. One thing that we can now do to actually be able to appreciate that why a tail current source is needed is that we can do the last signal analysis for this kind of a differential pair. And if we do the large signal analysis of this kind of a differential pair, we'll be able to appreciate that for a tail current source, the characteristics which are like this, where the gain is constant for a significant V common mode input range, here we'll find that it is not the case, right? And we'll be able to appreciate it when we do the large signal analysis of this guy, right? So for time being, we won't touch this just to save time, and and it is not a big thing to do. We can easily do that, but like if someone is watching and is curious, you can definitely try that out. Before we move any further, we should also discuss this or revise this lemma. that if a circuit remains linear, so the lemma here is that if a circuit is symmetric and I am holding the two ends of the symmetry, so if this point is a point of symmetry in a linear circuit, let us say this is some block which is linear, here is some block which is linear, and if I exert some excursion about this point of symmetry, so this node voltage will be V1 plus V2 by 2. Okay. And so for example, if I'm exerting a V1 exertion at this node and V2 at this node, so here we'll find the average. Why is that so? To analyze to like it's not a formal proof, but just to get it why that seems to make sense. So I take a very basic example of a linear network where I'm saying that this is my resistor, so we already know if this is R and this is R, we know that this point's voltage will be what? V1 plus V1 plus V2 by 2. So this is a fact known to us. So that it is just the extension of this idea that the circuit remains linear. And so for a small signal excursion in a basically in a transistor-based circuit, if I'm just exerting some small signal exertion about a point of symmetry, so that point of symmetry's voltage will be the average of the excursions. And this is a basic intuition as of why that seems to be, or why that not seems, but why that is true. Okay, so that being said, now we'll go to the next variation of the differential circuit, which is use of a degeneration resistor. So why are we doing this? We are doing this just with the sole motive, with the motive that we had basically even in a basic CS amplifier, that is to basically improve the linearity of a circuit. Because if you recall, the if I'm saying that this guy is V in 1 minus V in 2, so we know that for that the last signal behavior basically appears something like this, and we know that the amplifier is basically working as an amplifier in this regime only, right? Because here the outputs are saturating and here they are increasing linearly, which implies that only in this regime it is working as an amplifier. So if I want to increase this range of inputs for which it basically can function as an amplifier, I am using degeneration, and that's the basic idea over here also. And so we can quickly analyze that how will this guy behave. Nothing big has to be done here. Again, if you want to analyze the small signal behavior over here, the only thing you have to do is to just remove this guy. And now, again, as we did before, by superposition, we can analyze it. But do we really need superposition now? We already discussed the lemma. What was that lemma about? We said that if I'm exerting some excursion here, okay? So this node's voltage, I can find it as the average of these two excursions, right? Because the circuit follows symmetry. And so I can say that since in a differential signaling, this is V, if this is V8, this is minus V, so average is 0 here, I can ground this node in my differential small signal analysis, right? Which is quite amazing. And so if I were to take the difference of the difference of these two outputs, what will I get? I can just directly write that my minus del V out is what it is. If I just take minus common, it is minus GMR 1 plus GM RSS, and here what I'll have is V in 1 minus V in 2. Right, what I've done is I've just grounded this node and I've taken the output here because of this guy, I've taken output here because of this guy, and I've just taken the difference. And if I bring this over here, what I get is that my gain, my differential gain, here AV diff basically means my differential gain or gain to differential signal. So my AV diff here just happens to be minus GM 1 plus GM RSS, right? And again, here it should be noted that if I were to take output from either one of the terminals only, so I'm sorry. So if I were to take output from one of the terminals alone, we can understand and appreciate this that let us say that I'm taking output only from this guy and I'm applying some signal excursion over here. Okay. So now because I'm taking output only from one end, so we can intuitively say that yeah, the gain should halve. But let us now really try to look into the small signal picture, and let us say that let us try to see what will happen if you're taking output from only one side. And we already said that we can ground the node, right? And so here we are having this V in 2, here we are having this V in 1, and here we have here our V out 1, and here we have V out 2, but we are not taking this guy, right? And so the idea here is that if I were to describe that how will my gain look like, it will just be GM, GM R 1 plus GMRSS in response to V in 1, and this is my V out 1. What about V in 2? So so here we can see in this picture only that due to V in 2, the change in V out is basically the V out 1 is basically 0 in the small signal model, so I can just write minus 0, and here what I can write is what I can write. Yeah. So basically, I can just express it as V in 1. And yeah, so here I'm getting a bit stuck, I guess. But intuitively, we can understand that for a single-ended output, the gain must be a bit less, and we'll get back to it. And again, the problem with this particular circuit, there's some problem also with this particular circuit, and the problem here is that the problem is that there is a headroom issue. Why is there a headroom issue? It is there because if I just try to sketch the circuit all over again. So we already know that here some minimum voltage has to be maintained to keep this guy in saturation, right? And this minimum voltage will increase because now there will be some drop due to these two resistors, right? And since this supply is fixed, so we can understand that there will be some headroom issue. So the alternative to that is that we split the tail current source here and here, and we place the resistor here. So what happens because of this is that in the biasing, this resistor is ignored because for common mode signal, these two node potentials are at the same potential, and so this RSS plays no role. Whereas in differential signaling, these two guys open, and then again by symmetry, I can just halve this guy, and the differential gain more or less remains the same. So this is a great way to prevent the headroom issue. Okay. And in our last signal also, what we observe here is that because of this kind of a gain, which is reduced, we find it to be a more flattened out. So because without degeneration, the gain would have kind of been like this, and with degeneration, the gain is kind of like this, and over a larger range of of differential input. So that was is the basic idea. We will talk about so I think now it is also in order that we talk about common mode response also. Okay, I think it's pretty much in order, and also we will discuss about the single ended response. And we can now already understand this, that when RSS is equals to 0, it just reduces to a basic differential pair. So now it is makes more sense that we analyze our differential amplifier for time being with RSS included, because it's a more general case. Okay. So let us just try to analyze the common mode response, and keeping the lemma in mind, the lemma of symmetry in mind, because that is greatly easing our life. Because if you recall, before we were applying superposition and all, and again we are ignoring R naught, but it is just for convenience. We can include R naught also, but that won't give us a great deal of intuition in our analysis for time being. But when we'll analyze the same circuit with active loads. So there we have to inevitably consider R naught whenever necessary. Okay, so let us now analyze the common mode response. Again, it's a small signal response. So will ground the quiescent points, or basically rather remove the quiescent points, because for current we have to open it. Okay, and we have opened this guy, and I'll just place this R and R over here. And the question is that what can we do with this node? Now at this node, we know that we can't really ground this node because the average here is VCM, right? Right? So average here is VCM. So since we can't really touch this node, what we have to do is we have to consider some other route to analyze the circuit. But do we really need to consider some other routes? Now, notice that this circuit is entirely symmetric, right? And this means that this node is attached to this node potential is equal to this node potential, and this node potential is already equal. These two node potential are also equal, and this is RSS and RSS. So you should be able to understand that we can basically fold this circuit, right? Because even the inputs are same. This circuit is basically equivalent of this circuit only, and the GMs will basically add. And I think with this such kind of basics, we are seeing such kind of content are already clear that why will the GMs add, right? So GMs add, and this is our basically VCM signal, and so the GMs add, right? And since the GMs add, so we have this guy as 2GM, and now what is the common mode gain of the circuit? So if I'm taking my output over here, so you can understand that since in the small signal model, since we are using an ideal current source, there is no current signal flow allowed, which means that for any R value for VCM, no incremental current will flow, which implies that the common mode gain of this particular circuit, in this case for an ideal tail current source, is zero. So that is the benefit number two of the tail current source, which we can appreciate that for a tail current source, the common mode gain of the signal is again is zero, right? So if I were to write, so benefit number one was the range, right? The range of gain for V in or V common mode basically will increases. And number two here is that the basically it decreases ACM, because for let us say that the tail current source was not ideal and it had some resistance, let us say Rx. So even in this scenario, we can write the value of our gain. And what will that be? Again, it is just a CS stage with a source resistance, which is equals to 2 RSS plus RX, right? So we can just write it as twice of GM times R by 2, which is basically GM times R, 1 plus twice of GM times 2 RSS plus Rx. And we know that for tail current source, this Rx value is quite high. So basically, this gain value is pretty low. And this is our ACM. Okay. And now this one thing is clear to us. So now we can now appreciate the benefit of basically benefits of tail current. And we can understand that basically the range of input for which the gain is relatively constant is more, and the common mode gain also decreases. And now that being covered, let us go to another topic, which basically is mismatch. And we have already discussed this guy. So, what is basically mismatch? In all of this analysis, we have subtly assumed a very big thing, which is basically that in a differential amplifier, symmetry is there, which basically means that this R is exactly equal to this R, the threshold voltages are equal, the mobilities are equal, the transistor sizes, dimensions, everything is equal. And so this is a very big assumption of symmetry. But as we know, in our typical process and typical in fabrication of devices, there is always a certain skew. There is always a variation in devices that can be mismatched due to various reasons. It can be threshold voltage mismatch. It can be the beta factor, which is basically mu n times Cox W by L. That can be mismatched there, basically due to various things in general. It's a rather complex process, so we won't go into that why it all happens and all. So the basic idea is that realistically nothing is ideal, and thus even assuming that the system parameters are perfectly symmetric is also a big assumption. So because of this mismatch, the basic consequence of this mismatch is, so far what we were saying is that we don't want the common mode signal to get amplified, and that is something that we were achieving, which is fine. We also were saying that because by virtue of the symmetry, we were able to have some differential gain. Fine. But the consequence of this mismatch is that what happens is that even if you're applying some common mode signal, even if it gets amplified to certain degree, you can filter it out, right? Because it is, if it is, there is some common mode signal which is being applied at both the ends, which is typically of even, let us say it is of DC in nature, so you can block it out. But the problem will come when you are applying some common mode signal, which you are basically not applying, but it is being applied by the environment in terms of noise or whatever. And the problem will be that when that common mode signal will get amplified as a differential signal, because the idea behind differential signaling was that even if you are having some common mode gain, by taking the difference of the two lines, you are basically eliminating that common mode signal. But here, what is happening is that if you are taking some differential, if you have two lines that you are taking as output, here I'm talking about fully differential amplifier. And what I'm saying is that if you have along this line, you had some common mode gain, and here you had your small signal fluctuation, and along this line, you had some common mode gain, which again will be by the same amount, and again you had some small signal fluctuation. When you take the difference, the common mode signals basically cancel out, and in the end, by taking the difference, what you get is a normal differential signal output that you basically would expect. But the problem with mismatch is that what happens because of mismatch is that the common mode signal that you applied also becomes a differential signal. What I mean to say here is that if you applied some common mode signal at both ends, now it will manifest itself as a differential signal at the output side. How will you, so the way, so now you can't basically remove this output just by taking a fully differential input, right? It won't cancel out because now the common mode signal which got amplified is in differential form, and that is the basic consequence of mismatch. So basically, Razavi has discussed two kinds of mismatch separately. One is that he's basically discussing the mismatch in R, which is basically these load resistors. And second mismatch he's discussing is the GM mismatch, where the transconductance of these two transistors are different. Now, this GM mismatch can happen because of different mobilities, different maybe difference in W by L ratios, maybe because of difference in threshold voltages. So there can be various reasons to it. In fact, even a threshold voltage mismatch can in the end be modeled as a GM mismatch only. Great. So we will analyze this. Now CMRR also I have found various definitions for this. One, some people define it as gain to differential signal by gain to common mode signal. Some define it as gain to differential signals by gain of common mode to differential mode. So basically, the gain due to mismatch. But typically, this definition also works good enough. And this some another definition. So, common mode to differential mode conversion is way more problematic to us, especially when we are taking a fully differential output. But however, the desire to keep normal common mode gain less is also always underlying in our differential amplifiers, whether it be a single-ended or double-ended or fully differential. So let us talk about this also. And after we discuss the mismatch, no, we will just discuss the differential amplifier with some active loads. Okay, so let's do this. Let us discuss mismatch. So let us discuss R mismatch. So what we are saying here is that we have let us define it as del R by R. Here we have R. Here I'm naming this guy as M1, and here we are assuming that the tail current has some resistance Rx. And to keep things simple, I'll say that whatever the degeneration resistor we applied here, we have like ultimately merged it with this tail current sources resistance. And this is the incremental model because here we are trying to see that what is the gain at the output because of this mismatch, okay, due to the common mode signal. So now the my first fundamental question is that can we apply the lemma here that this guy's potential is basically equals to V in 1 plus V in 2 by 2. Here we can already understand that the fundamental symmetry of the circuit has broken down because of mismatch, right? The fundamental symmetry in the circuit is broken down. So how should we really approach this guy? One thing that we can do here is that see this node again is common to these two circuits. So what we can do is we can very smartly say that this guy is equivalent to RA 2RX in parallel with 2RX, right? And these two nodes are tied together, but now we can basically separate these two nodes. Okay. What I'm saying is that you can separate these two nodes out and you can basically express the circuit as something like this. This is how you can express the circuit as. Now, why I have expressed this circuit like this, or are we even allowed to express a circuit like this, or should I have had gone with some different approach? That's the question. Okay, I think this video is going a bit long, and we'll discuss in next video how to quickly analyze this guy. Also, I think we were stuck with one more little thing that was basically the analysis that we are basically were trying to establish that how for degeneration when we are taking single-ended input our gain should decrease, and we'll just try to quickly prove that also. So I think we will see that right away in the next video. And thanks again for watching, and we'll just wrap up this chapter in the next video. Thank you.